today is sort of the day where we make really strong connections between the graph of a polynomial function and its equation. Okay? Now, we started to do this on the first day that we looked at polynomial functions because we looked at things like the degree and the end behavior and the leading coefficients, things like that. Okay? And we were able to see some trends. And we're going to bring those trends in to the conversation that we've had over the past few days with the remainder theorem and the factor theorem around finding the zeros of a function. Okay? So that's kind of where we're going.
I just want to give you the stapler so I don't take it
Oh,
away from you.
thank you. You're going to make it onto my YouTube video. It's okay. You got to get close to the mic. Okay, so here's some things. Shh. Guys, if you came in late, sit quietly. You are now like 3 minutes late. No skin off my back as long as you don't take any skin off anyone else's back. Okay? All right, so what are some of the things that we might know about the equation of a polynomial function from its graph? Let's say we have a graph. What can we tell about the equation of the function? Okay, so we're thinking of any polynomial function. We have a graph of it. What are some of the properties that we would be able to tell? Yeah. What's that? Yes, we can tell if the degree is even or odd. We can also, a lot of the times, tell what the degree is, period, right? Because, for example, a linear function is going to be a line, a quadratic function is going to be a parabola. And so we can tell, okay, that one has a degree of 1, the other one has a degree of 2, etc. Okay, so we can tell the degree. And sometimes it's hard to tell the degree. Like, for example, if you look at y equals x to the 4, that's degree 4, but it looks like a very, very wide parabola. So sometimes it might not be so clear, but yes, you can definitely tell if it's even or odd. Because you can look at the direction where it starts and ends, right? If it starts and ends in opposite directions, it's an odd function. If it starts and ends in the same direction, it would be even. Okay, so we can tell the degree. What else could we tell about it? You may want to go back to like the first day. We're going to be reviewing some of that. Yeah?
Like from that, you can figure out the like the end, like the direction that it goes.
Okay, so what you're talking about is the end behavior, right? Yeah, which is kind of like, okay, what I want to know is that's something that you would visualize from the graph. So if you know the end behavior from the graph, what does that tell you about the equation?
Like the negative, or if the degree is negative.
Your leading coefficient, right? Yes, so we can tell the sign of the leading coefficient. And this is all by looking at the end behavior. Okay. There's something else that we can tell. Yes? Yes. So if there are factors, then we can tell what the factors are by looking at the roots. Okay. So, or we can tell the zeros of the equation can tell us about the factored form. Now, you have to be careful, though, because the zeros have to be rational for it to be factored, right? If you have to use like the quadratic formula to get a root that's an irrational value, then that wouldn't be factored. But if it's a rational root, like 1/3 or -2 or whatever, we can tell about the factored form, okay? That's if rational. Okay. What about the constant? If we wanted to know the constant of the equation, where would we look at the graph? Yeah, y-intercept, yeah. So the y-intercept is the constant. Okay, because essentially if it's a polynomial function, you're looking at powers of x. If you plug a 0 in for all those powers of x, everything's going to disappear except for the constant. Okay, and the y-intercept occurs when x equals 0. Okay, so I want to talk a little bit more about this guy. If you see a root in the function or a 0 of the function, you can tell a factor of the equation. Okay, now that's true. But we can also, depending on how that 0 looks, tell more about it. And we kind of hinted at this yesterday. Like, for example, is there 1 factor? Or is there 2? Or is there 3? So that's another piece that I want to talk about. And that's called the multiplicity of the root. Okay, or the multiplicity of a factor. Okay, so if you look at something like this, y equals x, then this has a multiplicity of 1. There's 1 factor of y equals x. And so the 0 looks like that. It basically passes right through. Okay, it looks like it's part of the graph, looks like it's part of the trend, passes right through the x-axis. Okay, this is a multiplicity of 1 because there is 1 factor of x. If you look at something like this, y equals x squared, that's our standard parabola. That 0 has a multiplicity of 2 because there are 2 factors of x within the equation. But because it's a repeated factor, we don't get more than 1 0. We still only get 1 0. Graphically, though, it behaves differently than this one. What does it do? Doesn't? Yeah, it bounces off. Right? So it doesn't, any sort of 0 with multiplicity of 2, or even 4 or 6 or 8, any sort of even multiplicity will hit the x-axis and bounce back up. And in fact, what's really happening here is that as the function approaches, as x approaches 0, the sign of the function doesn't actually change. When it crosses through the axis, crosses over, here it's negative, here it's positive, there's a sign change. But when it bounces back off, it's positive, positive, positive. For a brief instant, it's 0, which doesn't really have a sign. But then it goes back and becomes positive again. Okay, so there's no change in sign. Okay, multiplicity 3. So let's say we looked at, this is the multiplicity equals 2. If we looked at multiplicity of 3, I'm just going to do that here. Do you guys know what this one looks like? Y equals x cubed. Yeah, it's like, it looks like this. So it kind of goes like this. Okay, and so the multiplicity of 3, there is going to be a change of sign. Because if you think about it, let's say x is -1. You multiply negative sign by itself 3 times. That's still negative. Whereas on this side, if you do it a positive number by itself 3 times, you get a positive value, right? And so you have this sort of change in sign of the function whenever you have an odd multiplicity. However, with this cubic function, the graph kind of like slows down and then starts to speed up a little bit more. Okay, so it's not just like the sort of smooth graph continues. There's kind of like a dip in it. Okay, and this is called an inflection point, actually, this particular one. Okay, This guy is multiplicity of 3. Yes? Multiplicity is not the degree. It's the number of factors that you have of that particular factor. That's a good question, okay? So let me expand on that a little bit, okay? So let's say you have something that looks like this. Y equals x minus 1 times x plus 2 times x plus 3 squared. Okay? This has degree 4. It has 3 zeros. This one is multiplicity 1. This one is multiplicity 1. This one is multiplicity 2. Okay? Now, what is that going to look like? Well, so you kind of have to analyze a few things. So when I'm graphing this, the first thing I think about is where are the zeros? They're going to happen at 1, -2, -3. Okay? Then I'm also going to think, what's the degree? It's degree 4. Leading coefficient, positive or negative? Well, if you multiplied all these factors together, it would be positive, right? So we've got a degree 4 polynomial that's even. It's going to start and end in the same direction. And in addition to that, the leading coefficient is positive. So it's going to start up and up. Okay? Now at this one, it just touches and passes and bounces back up. Okay? So it's going to start up. It's going to touch, bounce back up. Now this is multiplicity 1, so it's going to go through. Also multiplicity 1, go through. Okay? So the multiplicity is not really the degree. It's the number of times that factor has been repeated. Okay? In the examples that I gave, yes, it was the degree because I only gave examples where there was one factor. Now, don't worry, we're going to break this process down. Okay? So let's take a look. Analyze the graph and determine. Okay, so we want to know the degree, the sign of the leading coefficient, end behavior, zeros, etc. Okay? So first, what is the degree of this function? 2. Okay. So if it's 2, even, it'd have to start and end in the same direction. But it starts up here and it ends down here. Yeah. There are 2 zeros there, though, right? So that's where people can get confused because they're like, there are 2 factors, but one of them repeats. It's not quartic, it's cubic. Okay, so how do you break this down? Well, so firstly, you can decide whether it's even or odd by looking at where it starts and where it ends. It starts up, ends down. So it's not even. Okay? And then you can sort of look at the types of zeros that you have, and sometimes also the types of sort of bumps. Okay? The maximum number of bumps that you will get in a polynomial function is 1 less than the degree. Okay? So here you have 1 local min, 1 local max. So that's 2 max mins. So the possibility is that it is a degree 3. Now this is a little tricky though, because depending on the function and the multiplicity of the zeros, you may get a cubic function that has no bumps, like this one. Okay? But we could probably have a pretty good idea that the multiplicity of this is going to be 3, because first it starts up, ends down, and if you examine the zeros, This guy, the way that it behaves indicates that that has a multiplicity of 2 because it goes down, touches, but doesn't pass through, bounces back up. Okay? Now, there is a very, very slight possibility that it could have a multiplicity of like 4, right? But probably if it would have to be even. If it's odd, it would pass through. But I think a multiplicity of 4, do you see how this bump and this bump kind of look like they're the same shape? A multiplicity of 4 would probably be more like this, more flat compared to that one. Like it would kind of be almost like a really elongated U. There would be a difference in the shapes in those two bumps, right? So there's a slim possibility that that could have some other multiplicity other than 2. It would have to be even, but probably not because it looks like that one.
For it to be a multiplicity of, like an even multiplicity of 3, it just touches the x-axis once, then is what you're saying.
If it's an even multiplicity, then it's going to bounce off. It's not going to pass through.
And then when it goes 4, then because it's wide, it would touch.
Yes, right? So one thing that sometimes is helpful to think about is single multiplicity, double, triple, quadruple. So if this is y equals x squared, y equals x cubed, and y equals x to the 4 kind of looks like this. It's really wide. Okay, so for example, I know that this is odd. Well, it's linear, but I know that it's odd. I know it's multiplicity 1 because as it passes through, it doesn't kind of level out and then go back up again.
It just passes through.
Yeah. Yeah. Okay. Now, there are very, very weird, like what ifs, weird scenarios where maybe you would get something a multiplicity of 4, but it would probably look pretty obvious that that's what you're seeing because this would appear differently, right? It would be wider, kind of like that. Okay? So what we can take from this, though, the degree is 3. Okay? What's the sign of the leading coefficient? Negative. Yes, because the end behavior is Q2 to Q4. Right? And here we can write that down. Q2 to Q4. Okay? The x-intercepts are the zeros. So there's a 0 at x equals -2 and at 3. And here, the multiplicity equals 2. Here, the multiplicity equals 1. Which means there is one factor of x minus 3 and 2 factors of x minus 2 in the equation. Okay, this function essentially is going to look something like this. We don't know what that leading coefficient is, but we know that it's negative. And then we have to have 2 factors of that, x plus 2 squared, and 1 factor of that. Okay. Y-intercept. What is the y-intercept? 1, 2, 3, 4, 5, 6. Yes. Okay. Now, in fact, you can use the y-intercept to figure out what that a value is, but we'll do that later. Okay. Now, the reason why we don't see it as a constant is because this is in factored form. Yeah.
For the y-intercept, the scale is like is 40. Is there 40?
Oh, shoot. Oh, you're right. You're right. Okay, wait. So how many little things are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, 18. That's got to be 20, right? Okay, so my bad. 2, 4, 6, 8, 10, 12. Thank you. You only go up to 8 when you do who do we appreciate. Okay. Interval where the function is positive. Where is this thing positive? Between Where's it above the x-axis? Here to here, right? Yes?
If it's on the x-axis, does it count as positive?
No, good question. No. So when we're writing out the interval over which this thing is positive, we do not include the zeros. It is not positive on a 0. 0 is neither positive nor negative. Okay? So the interval where the function is positive is, okay, so this is actually tricky because it's from here left, but not including that value. Does that make sense? Like it's less than 3, but it also can't equal -2.
It'd be in between 3 and -2, and then less than -2.
Yeah, so we actually have to do this in 2 intervals. The one interval is from -infinity to -2. And then the other one is from -2 to 3. But these are both exclusive. Okay? Now, how do you put that together? You use this symbol, yeah, that represents union. So we're unioning these 2 intervals. Okay? Now, that's not the only way that you could write this out. You could also say x is less than or equal to 3, comma, x cannot equal -2. You could do it that way too. Okay? What about the interval where this thing is negative? Yeah, positive, right? Or 3, or sorry, why did I do 3 to infinity? Okay. All right. Let's look at this question. So now our goal is to be able to graph this without technology. Okay? So there are a couple of important things that you need to think about when you're graphing this without technology. Okay? Number one, and some of these are sort of in no particular order, what is the degree of this function? 3. And what's the sign of the leading coefficient? Positive. If we were to expand it, it would be +1. Okay, so what that tells me is it's going to start here and end here in terms of the end behavior. Okay, because I always remember if the leading coefficient is positive, it ends in quadrant 1. And then if it's odd, it starts down. If it's even, it starts up. Okay, so the end behavior here is Q3 to 1. Okay, so that's some analysis that I want to do. Okay, another thing that I want to look at is what are the zeros and what are their multiplicities, because I want to make sure that if there's a multiplicity of 2 or 3 or whatever, that I draw that appropriately. Okay, so looks like one of the zeros is at 2, and one is at -1. Okay, and what about the multiplicities of those zeros?
1 and 2.
This one is 1, yeah, and this one is 2. Okay, so you may want to make a note here that it just touches. Am I spelling that right? Touch. Yeah, I think so. Okay, this one's going to pass through. Okay, now the other thing that's a useful point to have on there, because it will help to guide you when you're graphing, is what is the y-intercept. Now in factored form, the y-intercept is not necessarily obvious because the constant isn't going to be present in factored form. It would have to be expanded to see what the constant is. But instead of expanding, you can also just plug in x equals 0. That's usually the fastest way of doing it, right? So the y-intercept when x equals 0 is 0 minus 2 squared times 0 plus 1. And that is what? -2 squared times 1 is 4. So I'm going to put that point on as well. Okay, so now as I'm drawing this, I need to think to myself, okay, it starts in quadrant 3. Here, is it going to touch or pass through? Passes through, hits the y-intercept. What about here? Bounces off. Okay, so I'm going to draw that. And there's a pretty good sketch.
So if you have those elements, you don't have to worry about the rest.
Correct. Yes. Yep, I want to see the x-intercepts. I want to see the multiplicity very clearly. And I want to see the y-intercept. Yeah. Okay. All right. Let's try this one. Okay, so here, this is not factored. So we can tell a couple of things. We can say that it's cubic. Degree is 3. Leading coefficient is negative. What does that mean about the end behavior? Yeah. It's going to go Q2 to 4. Okay. How are we going to find the zeros here? Okay, so yes, in general, we could use the factor theorem, right, to try and start to factor. Is there a constant here, though? No, because this has a greatest common factor of x. So actually, the constant is 0. Okay, so depending on your polynomial, take the GCF out first. So this is going to be, and I'm going to factor out the negative sign as well, so that it's easy to factor the rest of it. X squared and then plus 8x plus 16. Okay, and then what about this trinomial? Is that factorable? Yes, probably. It is, and it's x plus 4 times x plus 4. Okay. All right, so what are my zeros? Correct. Negative 4 and 0. What about the multiplicity of this guy? 2. And this one is 1. Okay, y-intercept. Yeah, in this case, we actually have the expanded form as well, because we factored it. What's the y-intercept of that function? 0. No, it's, yeah, 0. It's all good, right? But if you plugged a 0 in here, then you're going to have 0 anyway, okay? All right, so we're going to set this up a little bit. I'm going to put my y-intercept in. I'm going to put my, and that's also an x-intercept, which is why it's the y-intercept. I'm going to put my other 0 in. And this one, okay, so first I got to start in quadrant 3. And then I have to end in, sorry, quadrant 2. Got to end in quadrant 1.
Quadrant
4. It's the last period for me on a Thursday. Okay. Yeah, I got to start here and here. I'm pointing at the right spots. I'm going to start in quadrant 2 and end in quadrant 4. Okay? So if I start up here and then I'm going to hit my first 0 at negative 4, do I go through or do I bounce up? Bounce up. Okay, then I'm going to go through, and that's it. Okay? Okay, actually, before we get into this, I just want to show you some interesting examples. Let's say I had, and look, I don't know if I'm going to ask you these or not. I'll have to think about it. But let's say you have this. This is just for fun. Okay. All right, so firstly, what's the degree?
It's just 6.
Yes, 6. Because there's 1 factor of x here, 3 factors of x, 2 factors of x, 6 factors of x altogether. Leading coefficient? Negative. Yes. So that is going to, it's even, negative leading coefficient. It's going to start here and here. Okay. I'm not even going to worry about my y-intercept. I guess I could, but let's just worry even just about the zeros here. What are my zeros?
Negative 2.
-2. 5. Okay. What's this one going to look like?
I don't know what 3 does.
We'll talk about that. Oh, sorry. Yeah, that's good. What's this one going to look like, though? It's a bounce, right? So it'll be like that or like that. Okay. This cubic one looks like y equals x cubed as it passes through 0. So this is, we don't know the direction yet, but it's going to either be like this or like this. Probably not. But you can. Like, isn't it cool that you know all this stuff now and you can just do it? This one's just going to pass through. Okay. So where does it start? Here. Yeah. And we're hitting this one first. So we're going to pass through. Then we're going to hit this one. We're going to bounce up. And then we're going to, like, do one of those. Isn't that cool? I would say, look, I wouldn't give you this one on a test because you could just plug it into your calculator and graph from your calculator. I would say I would give you parts of this, probably not all at the same time. But it's just so cool. Okay. Transformations. Okay, so look, there are a couple of basic polynomial functions that you should know roughly what they look like so that you can use transformations to graph, use your knowledge of transformations to graph transformations of those functions, right? So, like for example, I'm not going to talk so much about y equals x because we tend to be able to graph linear functions without transformations. But something like y equals x squared and y equals x cubed, you may be asked to graph transformations of those, right? Now, y equals x squared, that's quadratic. You've done that a lot already. Y equals x cubed, I think you know the general shape. It's helpful to keep a couple of points in mind, for me anyway, because then we can use mapping notation to graph the transformations, right? So I like to think of these 5 points because they're usually fairly small and easily visible in the window that we're given. Okay, so -2 cubed is -8. -1 cubed is -1. This is 0, 1, and 8. Okay, so just keeping some points in mind, just like when you're graphing a quadratic, you know, -2, -1, 0, 1, 2, and we remember 4, 1, 0, 1, 4. Same sort of idea, right? This is going to look like this. And this one's going to look like this. Okay, and then just keeping in mind all of what you know about transformations, right? So if you have y equals f of x, and that's transformed to y equals a times f of b x minus h plus k, then you can start from those base graphs, those base functions, and use your knowledge of transformations to come up with other points. Okay, so for example, let's say we take this function y equals x cubed and transform it to sketch this graph, y equals -4 times 2x plus 2 cubed minus 5. Okay, so this is actually in our form y equals a f of b times x minus h plus k. Okay, so if we can think about our mapping notation and what the value of all of those parameters are, then we can take our base function and find other points, connect them to make a graph. Okay, so So let's think about this. What are the transformations that are occurring to that function y equals x cubed? What are the transformations that occur to y equals x cubed to get this guy?
Vertical and stretch factor of 4.
Yeah.
And the x-axis.
And vertical reflection, yes. Horizontal stretch
1/2.
of 1/2.
2 left.
2 left. Yes. And 5 down. Okay? Now, the important piece, unless you're asked to list them, which you could be, is that you can do this mapping notation of x, y, mapping to 1 over bx, so 1 over 2 plus h, that's minus 2, and ay plus k, negative 4y minus 5. Okay? And then point by point, if I take -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8, if I can map these points, I should be able to get a pretty good idea of what the shape of my graph is going to look like. Okay, so let's see. 1/2 times -2. So -1 minus 2, -3. Okay, this is going to be 32 minus 5, right? 32 minus 5 is 27. Okay, all right. This guy, -1 times 1/2, -1/2 minus 2, -2.5, and then 4 minus 5 is -1. Okay, the point 0, 0, that one's nice and easy, -2, -5. And then 1, 1, 1/2 minus 2, -1.5, and -4 minus 5 is -9. And then finally, 1/2 times 2 is 1 minus 2 is -1. Oh, there's a pattern to those. That's so nice. Okay. And -4 times 8 is -32 minus 5 is -37. Okay, now we're not obviously going to be able to plot all of these, but we should be able to plot a couple of them. Okay, so -2.5, -1, -2, -5, and then -1.5, -9. Okay, now this is kind of an important point though, wherever the 0, 0 gets mapped to, because if we think about the original, if I put in the original, right? That 0, 0 is where it sort of flattens out. So I sort of want it to flatten out a little bit over there as well. It's a very, very steep slope though, so it's going to be hard to show, but let's see. It's going to go through there. When it's at -3, it's all the way up at 27, so we're not even going to be able to plot that. It's not even going to pass through here. And then there's kind of like a little dippy thing. There we go. A flattening. Okay. So far, so good? Okay. All right, so this is a common type of question. Determine the equation of least degree in factored form for a cubic polynomial. Well, that was a bit redundant, actually. Didn't have to put in cubic, because obviously it's going to be degree 3. With zeros of 1 and -2, sorry, -1 and 2, and the 2 has multiplicity of 2, and a y-intercept of -12. Okay. All right, well, let's start with these. If we know about the zeros and the multiplicity of the zeros, we can say something about the factors of the polynomial when it's in factored form. Okay? So from this, what are we going to know about some of the factors? We have a 0 of -1, multiplicity of 1. Yeah, you're going to have an x plus 1 to the 1. You don't have to put that 1 in, but it's a reminder, okay, multiplicity of 1. And then what else? Yes, x minus 2 squared. Okay, so there's going to be something like that in my function. What do I not know? What's that? The leading coefficient. Right, so I'm going to put an a in there. I don't know the leading coefficient yet. But I haven't used all the information yet. Yeah, the y-intercept is -12. That's a point. That is the point 0, -12. So I'm going to plug that point into my equation, and I'll be able to solve for the leading coefficient. Okay, so -12 equals a times 0 plus 1 times 0 minus 2 squared. And that is a times 1 times 4. Okay, so -12 equals 4a. So a is going to be -3. Okay, now once you get that leading coefficient, you can write out the entire equation. Do I want you to expand? I don't care, to be honest. Like, I'm trying to think, when you ask me that question, my mind goes beyond a test into what would we want to do with that?
Yeah, I can't really see anything.
You can't see it. Okay, so let me answer that. I would say that factored form, for the most part, is more useful, just because it's when a polynomial function is in factored form, it's very easy to graph. So look, if I don't indicate, you can do whatever you want, right? You can expand it if you want. You can keep it factored if you want. If I indicate one way or the other, do that. But if you're just working and doing something and this is part of a larger problem, off the top of my head, I would say most of the time, factored form is more useful to what we're going to do with it. Yes? Well, this might be a part of another piece of another function, like it could be the derivative of a function, and it might tell us, for example, where that other function is increasing or decreasing, or what the max-min values are, that sort of thing. And again, when it's in factored form, interesting things happen when this is equal to 0. So when it's factored, that's helpful because we can tell the x values where it might be equal to 0. That's a very, very 30-second short explanation. Okay, last question. Last question. 3 consecutive integers have a product of -210. Write a polynomial function to model this situation, then find the 3 integers. Okay. We're going to talk about it together. Okay, 3 consecutive integers. What does consecutive mean? Yes. One after the other. Yes. So like 2, 3, 4 are 3 consecutive integers. Yes.
So it would be like x times x plus 1.
Exactly. Yes. So what we're going to do is assign variable. So let the first integer be x. Okay. Then the second one is x plus 1, and the third one is x plus 2. Okay, now, the product of these 3 integers is -210. So if we multiply these together, now we have an equation, polynomial equation, that we can hopefully use to determine the value or values of x that sort of satisfy the conditions of this situation. Okay, so where do you think we should go next? Yeah, so here we're going to want to expand, because if this is equal to 0, that's great. Then we know the x values. But it's not equal to 0, right? So we need to expand this, equate to 0, and then try and factor so we can find those x values that work. Okay, so just quickly, this becomes x squared plus x, and then times x plus 2. Okay, so that's what? X cubed plus 2x squared plus x squared plus 2x equals negative 210.
We can do yesterday's lessons.
Exactly, yes. Exactly. So now we are going to equate to 0, x cubed. This is now plus 3x plus 2x, and then I'd have to add 210 to both sides, equals 0. All right, so yeah, if we want to find the x value that satisfies this equation, we ultimately want to factor this, because if we can find some factor x minus a, then the a value would be the one that makes this equal to 0. Yes?
Did you forget the square root of 3x?
Thank you, I did. No, because this is 3x. Yeah. It's okay, I make so many mistakes, it's very confusing, I know. Okay, there we go. Thank you. Okay, so let's think about what could potential factors be. What potential a values could we have so that x minus a is a factor? If x minus a is a factor, a could be yeah, but we should list the factors first. It's going to be factors of 210. There's a lot of them, right? So plus or minus 1, plus or minus 2, plus or minus 3. 4 doesn't work, 5. I sometimes find it easier when these really big numbers, I list the pairs of factors together. You know what I mean? Like 1 and 210, 2 and 105. You know what I mean? Yeah? I'll show, okay, so like plus or minus 1, plus or minus 210. Plus or minus 2, plus or minus 105. Because 2 times 105 is 210, right? Plus or minus 3, plus or minus 70. 4 doesn't work. 5 works, though. What's 210 divided by 5? I don't know. Thank you. Plus or minus 42. 6 works. 35, yes. Plus or minus 6, plus or minus 35, plus or minus 7, plus or minus 30. 8 doesn't work. 9 doesn't work. 10 works. Plus or minus 10, plus or minus 21. 11 doesn't work. 12 doesn't work. I think 15 works. What's 15 times 210 divided by 15? Does it?
14.
Oh, is it? Okay. 14 and 15? Okay, so this is done now. Do you guys know why this is done? Well, actually, it would kind of be like, I'd probably put the 14 on top. Okay, because you kind of go up 1, 2, 3, 5, 6, 7, 10, 14. We're checking that everything in between doesn't work. The next number you check is 15, but that's already down there. So now you have an exhaustive list. Yes?
If we got a question like this on a test, would you want us to list all of that?
Possibly. I wouldn't want you to test them.
Yeah. You want us to put it down?
Yeah. Okay, so look. Take my word for it. P of 7, I believe, works. No, must be negative 7. P of negative 7 works, because if it was 7, these would all be positive. So take my word for it. I'm not going to graph it, but if we look at P of negative 7, That's negative 7 cubed minus 3 times negative 7 squared, sorry, plus 2 times negative 7 plus 210. And that is negative 343. 3 times 49 is 147. Minus 14 plus 210. Nope. Did I mess something up? No, I think it's okay. What is that? Hopefully 0. It's 0? I think it's 0. Okay, I'm just going to check. Plus 147 minus 14 plus 210. That's 0. Okay, so what do we know? If p of 7 is 0, what's a factor? X plus 7 is a factor. Okay, so if we factor that out using synthetic division to see what else is possible, because sometimes you may have more than one solution that works. We will have a 7 here. I'm going to do my synthetic division. So this is 1, 3, 2, and 2, 10. Okay, so that's 1, 21. 3 minus 21 is negative 18. Uh-oh. What is that? 7 times negative 18. Negative 126. Negative. Did I mess something up here? This is a 7. I did mess something up. 1 times 7 is 7, not 21. 3 minus 7 is negative 4. Negative 4 times 7 is negative 28. 2 minus negative 28 is 30. 30 times 7 is 210. 210 minus 210 is 0. Phew. Okay. So to factor this, this gives us the coefficients of the quotient, x squared minus 4x plus 30. Okay. So when we start to pick this apart, we're going to get x plus 7 times x squared minus 4x plus 30. Okay. Now the question is, can we break this down? Because we got to keep going if we want to find all the solutions. Are there two numbers that multiply to 30 and add to negative 4? No. This guy is not factorable. So this is the only solution, is x equals negative 7. Okay. Now what does that mean about the 3 integers? Well, the 3 integers were x, x plus 1, and x plus 2. So x equals negative 7. X plus 1 equals negative 6. X plus 2 equals negative 5. And negative 7 times negative 6 times negative 5 equals negative 210. Yes? The x plus 2, the x plus 1 and x plus 2?
X minus 11 equals 6. X plus 2.
X plus 1. Right? Because the 3 original integers were, first is x, second is x plus 1, third is x plus 2. So far, the answers to the question are, what are the 3 integers that work? If we just solve for x, we've only said what the first one is. Yeah. Okay? There's other ways to make your let statement, though. You could say, let the largest integer be x, then the next two would be x minus 1 and x minus 2. But then when you solve the equation, you'd get a negative 5 for x, and so the overall 3 integers would be the same.
Wait, so how did you pick x plus 7 in the first place?
How did I pick it? Okay, this is how I picked it. Before class, I graphed it. And I saw on the graph that there was a 0 when x equals negative 7. Yeah. But algebraically, I should show that this is true. Yeah. Okay? All right, any questions? Okay, we're going to stop there.